All right, so our next section is going to be 6.5 properties of logs. You've seen a section or two like this, probably in Alg 2 and or pre-calc. The big difference is going to be we're going to look at problems that are a little bit more complex, they're a little more involved at times. This is going to be an expansion on stuff that should be a review. Okay, so real quick, properties of logs. We have 4 primary properties. The first is the product rule. So if I have the log base B of a product M times N, then this splits into the sum of the log base B of M plus the log base B of N. If I have a quotient, log base B of M divided by N, then this would split into log base B of M minus log base B of N. The power rule, if I have log base B of M to the P power, right, this power comes down in front as P times the log base B of that quantity M. And the reason that that works the way it does is because if I had this, it would be M times M times M times M. And with the product rule, I would split it up M number of times. And then when you add it, or P number of times, when you add it, you get P logs of M. Okay, so hopefully that makes sense to where that comes from. And the last one's the equality property. If I have like bases on both sides, single logs, so log base B of M equals log base B of N, then the only way this is true is if those two quantities equal one another. All right, this is just a rewrite of the exponential equality property from before. Now, one other thing I will add to this, with product and quotient rules, these work, all of them rather, work both directions for expansion and also to condense, right? So when I did it here, we expanded, but we can take something, if I have a sum of logs, I can condense it using the product rule. If I have a difference, I can condense it using the quotient rule. So the expansion to that I want to add is that when I have either sums and differences of logs, right, and I want to condense, anything that is positive when you condense it, assuming they all have the same base, anything that was positive goes to the numerator as a product. Anything that was negative goes into the denominator as a product. Okay. In terms of expanding, anything from the numerator gets expanded with a plus sign. Anything that came from the denominator gets expanded with a minus sign. Okay, so we can expand this. We can essentially have it grow into bigger problems. So expanding and condensing, right? Here's what I was talking about with the positives, negatives, and in terms of expanding and condensing. You're welcome to read through that, but I did just explain it above. All right. So if we're condensing to a single log, couple quick examples. All right, again, the bases must match for this to work. So here I have log of 5 plus log of 2. They're both base 10, so here I can get log of 5 times 2, which simplifies to log of 10. Now, I do still want to ask myself, can I simplify this? Here I have log base 10 of 10. That can be simplified. 10 to the first power equals 10, so this simply equals 1. My second example, I have log of x times 2, right? And if I rewrite that in a slightly more familiar way, this is the log of 2x. There's nothing I can do to simplify that any farther. We have a final answer. Now, in the last one here, I'm going to do a couple things all at once. Anything, like I said, that's positive is going to go to my numerator. Anything that's negative is going to go to my denominator. Okay. I'm also going to bring this 3 up as a exponent. All right. I need to really technically do that first and then condense it, but I can do it all in one step. All right. So here we're going to get the log of, in my numerator, x cubed times y, all divided by z. Okay. Now, if we look at the next example, the 3 log x is positive, but here both of these terms were negative. Okay, so I'm looking at individual terms. I could have another positive that comes at the end of this that would then go to my numerator. Okay, so each individual term, the sign of it determines whether it goes to the top or the bottom. So here, because the sign changed, we would end up getting log of x cubed over yz, right? Based on the positivity and negativity of these terms. All right. If we're expanding, same thing. I want to expand it, and then once I have it expanded, I want to use power rules, if applicable, to bring exponents down in front as coefficients. So the first one, log of 2x, this would be the log of 2 plus log of x. Because it was a product, they were both in the numerator, they split up as positives. Here I have log base 5 of x squared y, right? So here it should be log base 5 of x squared plus log base 5 of y. And really, you could have done both steps at once. I want to still bring this coefficient down as a, or this exponent down as a coefficient rather. So we're going to have 2 log base 5 of x plus log base 5 of y. In number 3, all right, numerator, denominator. So when I split this and expand, we're going to have the following. We're going to have log of x plus log of y and minus 3 log of z, if I do the double step there. Okay, and the last one will follow the same pattern. So here we're going to have log base 2 of w plus 2 log base 2 of x minus 2 log base 2 of y and minus 4 log base 2 of z. Okay. Condensing to a single logarithm. Okay, we can have some big, messy, crazy things going on here. This one we're going to condense. We're not necessarily going to simplify the quantity we're going to get when we condense it. But because this has so many moving pieces, I'm going to do this in a few steps. Okay, first and foremost, I want to bring up my coefficients as exponents. All right, so when I do that, I'm going to have log of 5 plus log of x to the 1/2 minus log of 7x minus 1 and plus log of x minus 1 cubed. Anything that's positive, I want to condense to my numerator. Anything that's negative is going to go to my denominator. So here I'm going to end up with log of 5x to the 1/2, or 5 square roots of x, times x minus 1 cubed, all divided by 7x minus 1. That is a single condensed log for this expression. It's big, it's messy, all right, but I can still condense it, possibly for the purpose of trying to solve something in the future. All right, expanding from, again, in this case, a messy condensed log. So I'll do this in a couple of steps. Again, anything numerator is going to be positive, negatives are going to be, or denominators are going to be negative. So here we would end up with natural log of, and I'm going to rewrite this as x minus 1 times 2x plus 2 squared, all to the 1/2. All right, I'm going to write that square root as a 1/2 power, minus the natural log of x squared minus 9. Okay, it is important that I put parentheses around this because x squared, if you just had natural log of x squared minus 9 without parentheses, it would only think the x squared is part of the log. Okay, from here I can take, with my power rule, I can bring this 1/2 down in front as an exponent, or as a coefficient. So I would have 1/2 natural log of, and it's really the product, x minus 1 times 2x plus 2 squared minus natural log of x squared minus 9. I want to split this using the product rule, but remember it's 1/2 times all of it. So I'm going to have 1/2 times natural log of x minus 1 plus, and I'm going to bring that exponent down to natural log of 2x plus 2 minus our natural log of x squared minus 9. Last thing I can do, I can distribute this 1/2 back in. Will give me 1/2 natural log of x minus 1 plus natural log of 2x plus 2 and minus natural log of x squared minus 9. That is as expanded and simplified as I can get for this particular logarithm. Okay. Primary reason that we use our properties of logs is so that we can either simplify it simply to, rewrite it in a more condensed package, but usually it's going to be so that I can either evaluate or that I can solve something. So here I have this particular expression. Right now I want to solve it. I can solve each individual piece here, or I can rewrite a few things. All right. So here, if I wrote, it would be log of 5 to the log base 5 of 1 to the 1/2 power minus log base 5 of 5 squared. Okay. 1 to the 1/2 is square root of 1, which is simply 1. So here I have log base 5 of 1 minus log base 5 of 5 squared is 2 because these cancel. All right, in terms of log base 5 of 1, 5 to the what power equals 1, it's going to be the 0 power, so I have 0 minus 2, or this expression equals -2. Again, so here I was able to use a bunch of different properties. This is not the only way I could have done this. I could have used quotient rule, rewritten it, and I could have done some things like that to make this work as well. It's a matter of, which way do I want to do it, which way is going to be simpler for the purpose of which I'm doing a particular process. All right, when we're dealing with logs on both sides, I do need to work to condense to a single log usually. Okay, so let's take a look. I've got another one here for you guys to try. You guys can do that on your own. I'm not going to go through and do a second one of those right now. Next thing we need to talk about is the change of base formula. All right, I could take really any log that I want, log base b of x, right? The only two log bases that our calculators work with is either the log base 10, right, which is just our regular log, or the natural log or log base e, okay? As a result of that, our final answers need to always be written in either natural log or log base 10. So what we do, right, the base of my original log becomes the base of my fraction when I split it, and the quantity of my original log becomes the numerator. Okay. Now a slight expansion to this property, right, is that really the log base b of my quantity x, I can rewrite into any log base. Now, typically we're going to use it with natural logs or log base 10, but in theory, I could write this in any log base a of my original quantity x over log base a of my original base b. Okay? So I could write it into log base pi if I wanted to. The place where this actually sometimes pops up is maybe you get some quotient written like this in some really weird funky base, and you can rewrite it using change of base backwards into a single condensed log that when you have the new or the original bases and quantity, if you will, is something that you can simplify. Okay, so I just want to point that out because it is something that does come up from time to time in solving in a way that I can simplify to make something work for us. So if I have a couple things that I want to evaluate, especially if I wanted them in exact form, here I have log base 4 of 15. Now think about approximations of logs. 4 to the first power is 4, 4 to the second power is 16. So here I should be expecting as a decimal some value that's going to be a little bit less than 2, right? So here, whether I write it as log of 15 over log of 4, or I could write it as natural log 15 over natural log of 4, right? Either way that I do this, all right, so if I use log of 15 divided by log of 4, right? I'm going to get 1.953. If I did that with natural log, right, I get the exact same decimal approximation. And just to show you that it matches log base, if I had log base 4 of 15, right, again, I also get the same approximation. If for whatever reason, if I wanted to rewrite it in, like I said, log base pi of 15 over log base pi of 4, I could do this, right? It's going to be log base pi of 15, then all divided by, oops, hold on, why is it doing that? Well, it was giving me an extra parenthesis there. All divided by log base pi of 4, right? And I get the exact same answer, okay? So we could do this with all of them. Log base 20 of 4 here. I'm going to have something maybe natural log of 4 over natural log of 20. Oops. Extra parenthesis in there, and I get 0.463. Okay. So again, I'm not going to insult your intelligence by doing 2 more of these. I don't think we need to. Again, make sure for final answers, if it's an exact form or if it's asked for an exact form, that you do in fact put your final answer in either log base 10 or natural log. Okay. Evaluating and solving logs, right? So if I have something like this, okay, so let's say we've got this problem here. Oh, it doesn't want to, there we go, gave me a straight line finally. Okay, I need to rewrite as a condensed log, right? We're looking on the left here. All right, single log on each side possibly. In this case, I have a single log equals a number. I can simply go through and roll the log. Okay, when I roll the log here, I'm going to have 2 to the 3rd power equals x plus 3. Or 8 equals x plus 3. And we get x equals 5. Right, the only thing I want to do is check this x equals 5 back into my original logs. Right, really what I'm looking for the most part for extraneous solutions, here I don't have one, is making sure that this quantity then is still positive. 5 plus 3 is going to give me 8. We're good to go. Okay. If I take a look at my second one, I have a log on each side. I have a single log on each side. The bases match, which means I can use that log equality property. The only way this statement is true is if my two quantities equal, so 2x plus 7 equals 3x minus 1. And when I solve, here we're going to get x equal to 8. Right, and again, if I were to check my work, I'm going to get a positive log on each side. I am going to get something that does work. We are going to be good to go. On the left, we're going to get log base 2 of 23, and on the right, we're going to get log base 2 of 23 as well. So this does work out. Next example I have here is log of 27 equals log of x plus 2 log x. Now I've got multiple logs going on here. I can do this as a single log on each side, or I can get everything onto one side and roll the log. I'm going to do a single log on each side. All right, I'm going to bring this coefficient up as a exponent, and I'm going to condense all in one step. So here we're going to have log of 27 equal to log of, it's going to be x times x squared, which is really x cubed. So here I have single logs, same base on each side. The only way this is true, log equality property, if these quantities equal, so here we get 27 equals x cubed, and if I take cube root each side, we get x equals 3. Okay. Again, if I plug the 3 back in, we're going to be good to go. All right. Here I would have essentially 3 log of 3, and on the right, or on the left, I could rewrite this as 27 is 3 cubed and bring that 3 down, and I get 3 log of 3, which would equal my right hand side. Okay, so if you were verifying it, you could do it that way as well. Okay. The next one that I have here, again, we're going to condense on the left, so we're going to get log of x times x plus 2 equals log of 8. If I simplify this quantity in the brackets, right, while I do the next step, which I have base 10 on each side in a single log, I have x squared plus 2x equal to 8. I have a quadratic, I need to solve it, so I have x squared plus 2x minus 8 equal to 0 because I need it set equal to 0. I need two factors that multiply to negative 8 and add to positive 2. They're going to be x plus 4 and x minus 2. All right, giving me solutions of x equals negative 4 and x equals positive 2. Now here, if I go back and look, okay, when I excuse me, plug the negative 4 back in, here I have log of negative 4, and here would have log of negative 2. I'm not allowed to take a log of anything that's negative. This answer is extraneous. The x equals 2 does check out, so we're good to go here. Typically speaking, right, not always, logs are one-to-one by themselves. When I have a sum and difference of logs and some other things, we can get some instances where you get multiple solutions, okay? But as a general rule, logs are one-to-one if it's a single logarithm. Most of the time with these answers or with these problems, you're only going to get a single answer. Now, think about what the logs look like, right? Depending, okay, so here's a sketch of my log graph, right? It is possible, right, if I have a log and it's equal to another log, there's probably only one point of intersection, but maybe not necessarily. If I had a log that was shifted over here, it was very steep, I could get something that's like that, okay? So when I start throwing multiple logs in here, it is possible that we get more than one point of intersection, okay? Or possibly even if I took that same log right here, right, and I move it down here, we're going to have no intersection. We could have a no solution, okay? So again, logs are one-to-one. Generally speaking, we should expect one answer, one solution. However, we could also get 0 solutions. We could get possibly 2 solutions, okay? We need to check always for extraneous, as they can happen. They can happen in pairs or singles. There are different ways that could occur. All right. This one here is the same problem. All right. The last example here that I have for us is an application of logarithms. This is dealing with pH. All right. So acidity. All right. So the acidity or pH of a substance is given by the formula below. And that formula is the pH equals the opposite of the log of the hydrogen atoms. And what we're really looking at is the concentration of hydrogen atoms. Okay. Excuse me. So here what I've got and what I want to ask is, if the concentration of hydrogen atoms is quadrupled, what is the effect on the pH? Now, we're going to circle back around to this here in a minute, and I'll show you where it comes from and kind of explain it. But in this case, it really doesn't matter what I start with, okay? Which might not make a whole lot of sense right now, but it doesn't matter whether I have a pH of 4 or a pH of 10, okay? Or if I have a pH of 1, something that's highly acidic, right? The lower the number of pH, the more acidic it is, okay? In this case, it doesn't matter, right? So I already have written here pH equals the opposite of the log of C, right, for the concentration, right? And it's the concentration of the hydrogen ions, which is why the original formula is the H+, okay? So let's say I take my formula that I have written here, right, and I adjust this, and I make my pH equal to the opposite of the log of 4 times whatever my concentration C is. Now I'm going to do a little bit of manipulation here. I'm going to expand this on the left, or on the right rather, using my product rule. So I'm going to have the opposite of the log. Actually, let me do this. I have the opposite of the log of 4 plus the log of C. If I distribute that negative, right? So my pH is going to be the opposite of the log of 4 minus the log of C. And let me do a quick little rearrangement here. So I have a pH that's going to be equal to the opposite of log of C, right, minus the log of 4. Well, notice that, oops, I forgot the C. I said it and I never wrote it. All right, so here I have the opposite of the log of C, right, minus log of 4. So right here, the pH of the opposite, or pH equals the opposite of log of C, that is my original equation. So when I quadrupled the hydrogen atoms, or the concentration of hydrogen atoms, or ions rather, what I end up with is my original pH concentration here minus a pH of log of 4. So if I evaluate log of 4, right, think about it, 10 to the what power equals 4, right? It's going to be less than 1. Here I'm going to have negative 0.62. So we're going to have pH equals the opposite of the log of C minus 0.602. So a quadrupling, or 4 times the concentration of hydrogen ions, right, is only going to drop my pH a little over half of a pH marker. Okay, it's going to drop it by 0.602. Right. The reason for that is much like Richter scale for earthquakes. Right. That's also logarithmic based, such that pH, for us to lower the pH or increase the acidity by 1 pH marker, to go from a pH of 4 to a pH of 3, the pH of 3 is 10 times more acidic, or it has 10 times the concentration. To go from a pH of 4 to a pH of 2, it is 100 times more acidic. And to go from a pH of 4 to a pH of 1, it would be 1,000 times more acidic. All right. Think about it. To go from a pH of 14 to a pH of 1, it would have to be 10 to the 14th times more acidic. Okay. Or excuse me, 10 to the 13th times more acidic. All right. Everything here is by a factor of magnitude of 10. All right. Very much like, again, earthquakes with the Richter scale. A magnitude 7 earthquake is 10 times more powerful than a magnitude 6 earthquake. Okay. If you've ever experienced one, or if you've ever felt one, it's a very interesting thing, right? But to also then feel and experience a small tremor or earthquake, and then see on the news or look it up and find out that hey, that was a magnitude 3.1, and you're like, oh wow, like it actually moved the earth, and a picture on the wall kind of wobbled and shook. And then you think about the fact that a magnitude 4 is 10 times as strong, and a magnitude 5 is 100 times as strong, and a magnitude 6 is 1,000 times as strong. It really starts to put that into perspective of how intense something like a magnitude 8 or a 9 earthquake would actually feel like. Okay, so we may see a couple of things that deal with magnitudes and earthquakes, which is why I'm kind of talking about it a little bit. But we will also probably see a few problems that deal with pH as well. Right, that's all I've got in terms of notes for us for today. So take a look at a couple of the problems in the book. Maybe try a few ahead of tomorrow. That way, if you have questions, you're able to ask them during class tomorrow. All right, have a great day.